5 exponent 6 divided by what? 6.5 exponent 6 plus what? 500 exponent 3. Okay? And this one is square. So when you do your computation by using your scientific calculator, you will find that acceleration due to the gravity on the satellite's surface is 8.29 meter per second square. So 8.29 meter per second square. That's the value for acceleration gravity on there. So you say that therefore the acceleration due to gravity on there at any point along the satellite orbit at any point along the at any point along the satellite orbit is 8.29 meter per second square. So G is 8.29 meter per second square. Make sure that you get that value. Okay? Interesting. So that's the value of acceleration due to the gravity. Then part 2, wanted to leave part 2 for you. Let me help you. Then Roman 2, so that is, this is Roman 1. So this is Roman 2. Okay? So Roman 2, we say that you want to find centripetal acceleration. Centripetal acceleration. So you have to be careful here, especially with this concept. You might say that, you know that this concept of centripetal acceleration is a little bit difficult because I didn't learn about circular motion. No, that's not an excuse. Even if you learn a circular motion there, you have to think. Okay, you have to think. So we'll be following a number of steps on achieving this. We ended in 6 steps, so this is 7th step because we are still solving the same problem. We say that you have to recall the formula. You have to recall the formula of what? Centripetal force. Centripetal force. So with the formula of centripetal force, we say that this is mass times velocity square over radius. So remember that the centripetal force, the satellite is the one that will be providing the centripetal force to the S surface. So that's the force. But also remember from the second Newton law of motion, we say that force is equal to mass times what? Acceleration. Okay. So in case that you want to get acceleration from this second Newton's law, right? So I mean that, for example, that you, okay, so it's according to the second Newton's law, we used to say that the force is equal to mass times acceleration. If you want to make acceleration a subject, then you have to divide by mass. So acceleration is equal to force over mass. So this is the formula for accelerations according to the second Newton's law. But that is not all about what is centripetal. What is centripetal? Centripetal acceleration. So, if that the case now we say that the centripetal force also will be given as mass times centripetal acceleration. So suppose that this is equation 2, and suppose that this is equation 1. So if you compare equation 1 and equation 2, if you compare equation 1, so that will be the 8th step, because you have to understand the 8th step. We say that if you compare, if you compare equation 1 and the equation 2, then you will find that the centripetal acceleration is equal to square of the velocity of r. Interesting. Okay? Is equal to that one's of what? Of r. So if this is square of the velocity of a radius, then we say that for the satellite now, for the satellites we've been talking about, we say its r is equal to radius of the s plus what the h. So we say that the centripetal acceleration is equal to velocity square, then radius of the s plus what the height h. So this is what you've been looking for. So do we know the velocity of the satellite? Do you remember the formula for the velocity of the satellite? I told you in previous lectures. So recall the formula for the velocity of the satellite. Because if you know the formula for the velocity of the satellite, and then now you can find the centripetal acceleration. So the 9th step, we call the formula for the velocity of the satellite. Right? So do you remember it? So I taught you 2 formulas. One of the formula is, you can derive it or you can recall it in case that you remember. So one of the formula we say that it is radius of the s times square root acceleration gravity, then times radius of the s plus the height h. So this is equation 4. Why? Because this is equation 3. Okay? So that's the formula for the velocity of the satellite. Good. So if this is the case now, we say that if you find the square of this velocity of this formula, we'll get e square, and then g of 40, radius of the s plus 40, height h. So this will be a 50 equation. So the relationship between the 50 equations, or substitute the 50 equations into it. This is the third equation. We have the third equation here. So you got the 10th step. 10th step, we say that we have to substitute equation 5 into equation 3. So if you do such substitution, we say that the centripetal acceleration is equal to what? Square of that velocity, which is radius of the s square times acceleration gravity. Then here we have radius of the s plus h, or plus height h, then divided by this expression. So that's the v square. So divided, so if you divide, so it means that we say that divided by what? Radius of the s plus the 8h. So V square, square of that ones. Okay. So centripetal acceleration is equal to radius of the S squared G over radius of the S plus 8h divided by this over 1. So which will be squared if you do that division. Okay? So then this is the formula to determine the centripetal acceleration. Radius of the S will be given as 6.5 exponent what? Exponent 6 square. This is acceleration gravity on the S surface, not on the satellite surface. So then this we multiply with 9.8 meter per second square. This is meter. So this is meter per second square. And then we divide with some 6.5 exponent 6 meter plus 500 exponent 3 meter. But this one also should be squared. So we have meter square, no, we have meter square, so this is squared. So we have, yeah, that is squared K5. So here we have meter square, and this meter square will cancel, remain with meter, and then per second. So centripetal acceleration, you have to use your scientific calculator to do your computation. And then finally, if you do such kind of the computation, you will find that centripetal acceleration is 8.45 meter per second square. 8.45 meter per second square. Therefore, we say that the centripetal acceleration. So you see, you understand now why did I write the concept, okay, acceleration of, okay, the centripetal accelerations of the satellite, or provided by the satellite, is 8.45 meter per second square. So that's the response of that question, because the centripetal accelerations of the satellite. Do you enjoy the beauty of physics? Physics is beautiful, and special mechanics is beautiful. And this we call it classical mechanics. So then now I have another question, very interesting question, from the book called the Advanced Physics, and the author is Roger Mancaster. Okay? So let me give you that question. Write that question on the blackboard for you. The question, this is example 11. Refer Advanced Physics book by Roger Mancaster, page 136. Question A, 13. A 131 at the end of rinsing, and this is the concept. The orbits of the S end of the Jupiter orbits of the S and the of Jupiter are very nearly circular. With radii of 150 exponent 9 meter, and the 778 exponent 9 meter respectively. So Jupiter Jupiter's period around the Sun is 11.8 years. Roman R show that those figures, which figures that will be given, those figures are consistent with Kepler's third law. Kepler's third law. B. Taking the value of gravitational constant of the gravitational constant take the value of gravitational constant G to be 6.67 exponent -11 Newton meter square per kilogram square. Estimate the mass of the Sun. So the questions is very simple. Just testing you the understanding of previous lectures of gravitation. So the questions say that this is Roger Lancaster. So here it is Roger Lancaster by Roger, very important book. Roger Lancaster. Page 136, you'll find that question. Okay, so I didn't mention those reference books just like fun. No, I mentioned because they are very useful. You have to refer them, so you have to solve problems from those textbooks, from the questions and answers books, many problems as well as you can. So the orbits of the Earth and of the Jupiter are very nearly circular, with radii of 150 exponent 9 meter and the 778 exponent 9 meter respectively. So this is the radii for the Earth, and this is the radii for Jupiter, right? The Jupiter's periods around the Sun is 11.8 years, the periods for the Jupiter. Then ensure that these figures are consistent with Kepler's third law. So first of all, you should know the mathematical equations of the Kepler's third law. Otherwise, you won't solve that problem. Then, part B, taking the value of the gravitational constant G to be 6.67 exponent negative 11 Newton meter square per kilogram square, estimate the mass of the Sun. I taught you this, so this is just like a review of what I taught you in lecture 4. Okay, lecture 4, something like lecture 4 or lecture 3, between there. I don't remember exactly which lecture, but lecture 2 or lecture 3 or lecture 4. So this is your homework. So this part B is your homework. But I will help you part A, because something you might think that Olenjolai is solving, is leaving many difficult questions and using difficult language. So for us to try and see that physics is difficult. No, that is not my intention. My intention is to challenge you. My intention is to tell you the truth about the world of advanced physics. So solutions of question 11A. I have to answer that. I have to teach you how you can show that these figures are consistent with the Kepler's third law. So the first step, you have to recall the mathematical equation or mathematical formula of third Kepler's law. Kepler's law. So it's mathematical. We say that the square of the period is very proportional to the cube root of the mean distance. Right? That's what we have discussed. The square of the periods of the satellites, or the square of the periods of the planet, is directly proportional to the cube root of the mean distance from the year between the year centers. So that's what we say. And then if we want to write this law in mathematics, we have the proportionality constant K, then you have R cubic. So that's the radius of the planet. Okay. So again, we say that this is square of the periods over cube of the radius. This will give us Kepler's constant. Okay? So Kepler's constant. So we go for the second step now. Okay, to show that these figures for the Jupiter and Earth are consistent with the said Kepler's law, is when we'll be calculating the Kepler's constant, proportionality constant, okay, and by using the periods of revolutions of the Jupiter around the Sun and its mean distance. Also by using, we have to compute the value for the proportionality constant, Kepler's proportionality constant, by using the periods and the mean distance of 40 of the S. So in case that we find that we have the same constant, then the figures are consistent. That's the meaning. So the second step, we say that compute the value of proportionality constant, okay, by using the period and the mean distance of the S. So it means that the period of the S, how long does the S take to complete one revolution around the sun. How long does it take? You know. It takes how many days? How many? 1 year. Okay? So it takes 1 year. And then the mean distance, or the radii of 40 of the S, the radii of the S, it has been given as 150 exponent. This is the distance from the S is from the center of the S to the sun, exponent 9. So this is the distance from the S to the sun. So then, in case that you want to find this proportionality constant, you have to take the period, which is 1 year, and then we square, and we divide with 150 exponent 9 meter, and then this one is cube. So you have to use your scientific calculator properly. So the unit here of K will be here square per meter cubic. So use your scientific calculator to compute the value of that proportionality constant. So by using your scientific calculator, the value of proportionality constant for that case of the S will be 2.967 exponent negative 34. So negative 34 years square per meter cube. Go for the steady state. Steady state, we say that compute the value of what? Of proportionality constant by using the period and radius of the Jupiter. So this proportionality constant, period of the Jupiter, over radius distance from the center of the Jupiter to the sun. So the period of the Jupiter is 11.8 years. So this one we have to square. The distance from the center of the Jupiter to the sun is 778 exponent 9 meter. This one you have to find the cube. So use your scientific calculator to determine this proportionality constant. You'll find that it is 2.957 exponent negative 34 years square per meter cubic. So from those values, you find that in both cases, we found the value of proportionality constant. Value of proportionality constant is the same. So because these values are the same, then we say that the figures are consistent. So we say that therefore, hence shown, or even if that we say that K computed on the Earth's surface is closely equal to K computed on Jupiter. So therefore we say that hence shown that the figures are consistent. Consistent because the value of K is the same when the S and D, when the S and the Jupiter are considered. Okay, so because the value of proportionality constant is the same in both planets, if you consider the S planets and the Jupiter planets, so then you say that the figures are consistent. It means that they are consistent according to the law, and then you enjoy your moment because you have managed to solve part A of problem 11. So make sure that you do all the homeworks that I've given. So left two questions for this lecture. Make sure that you do before you continue watching lecture or session or period 7, period 8, because the next lecture will be either lecture or session or period 8. So make sure that you do those questions. In case you find that you didn't understand any point, repeat this video as several times as you can for you to understand. Sometimes maybe you might find that I'm going very fast, but that's the beauty of digital technology, because you can pause the video, you can repeat it, you can watch it twice, 3 times, 4 times, 5 times, until that you are satisfied and you find that now you have understood what it has been taught. Okay, so I would like to thank God who have been with me from the beginnings of preparing this lecture 7, and even now that he has been with me, that during I've been teaching you, and I would like to thank you also for taking your time. I know that was a little bit challenging time for you because this stuff are new for you, so you might find that maybe you get surprising that whether this is stuff the way they are, but that's why that I give you the reference books that is so you can go through. So thank you very much. I would like to ask you that watch some other videos of previous lecture 1 to lecture 6, and also watch the next videos of lecture 8 onwards, and make sure that you subscribe and you share these contents to your schoolmates, to your classmates, to your friends, to your young brothers, to your young sisters, and also don't forget to tell us where are you watching from, because this is a national program and we are very interested to see that the programs help thousands and thousands of students from our beautiful country, United Republic of Tanzania, and even from African continent. So in comment section, please tell us you're watching or you're enjoying this material where in the world. Okay? So thank you very much. See you in the next lecture.